Haiti and our approach for detecting on energy losses in the microgrid. As mentioned, this is follow-up work from last year's IPSN, and it's being done by me and my colleagues at CMU and our friends at SparkMeter, which is a CMU spin-out company. I have to say this, their mission, official mission is to provide flexible and high-fidelity energy management for grid operators. Okay, so there. So in case anyone is unfamiliar with microgrids, a microgrid is essentially a small-scale electric grid. And in many cases, microgrids use multiple forms of distributed generation. So we're talking about diesel, solar, wind, or battery power. And the reason that we care about microgrids is there are 1.2 billion people in the world who don't have access to reliable electricity. And we think microgrids can be a very cost-effective and just generally effective solution for solving this or helping alleviate this energy poverty problem. So here we see a rendering of the actual microgrid deployment in the rural town of Les Anglais, Haiti. At the time that the first paper was published, we had 50 households that we had connected to a 12 kilowatt diesel generator. The diesel generator runs the only cell phone tower that they have in town. And so the idea was to use the excess capacity to power a couple of homes. Now, over the last 2 years, we've gradually expanded the grid to include a bunch of things: 93 kilowatts of solar generation, 30 kilowatts of diesel, 450 kilowatt hours of lead-acid battery storage. And we are currently powering 439 customers, 3 of which are commercial customers. So their usage limit is above 1 kilowatt. And most of the customers are much lower than that. So they have a limit of like 30 watts. They're using the electricity to charge their cell phone, for instance. And along with this microgrid, SparkMeter has also on the side gone off and started 2 other small deployments, one in India and one in Nepal. So when we're talking about the detection of losses in microgrids, what exactly are we talking about? To be more precise, we're looking at non-technical losses, or NTL, as it's known. NTL normally includes 3 things: energy theft, non-paying customers, and unmetered homes. So this is as opposed to technical losses. Technical losses are things like resistive line losses. You can't completely get rid of resistive line losses. So that falls under technical. NTL can be pretty dangerous. A small microgrid can get into a vicious cycle where a little bit of NTL causes you to lose money as a grid operator, and then that makes your service worse, and that in turn makes people steal even more because your service is so bad. So this this kind of detection of NTL that we're doing, we don't know of a system that really does things in the same way. All right, I will try to go over the whole architecture in 1 minute. Let's see how I do. So we have the first part of the architecture. There are 3 main parts. First part is the gateway complex. So that provides local storage and communication between this grid and our Amazon AWS servers. There's the cell phone tower complex. That provides the GSM connection to the outside world. It's the only internet connection in the system, and it also provides some of the diesel power. Lastly, there's the energy meter network, which is a multi-hop TDMA network based on IEEE 802.15.4. And it's made up of meters mounted on the outside of people's homes and forwarders mounted on the tops of utility poles for large coverage. The meter hardware is completely custom, and it's really useful for maintaining grid stability because it includes a digital fuse in every meter that can be used to turn off individual houses. So for modeling the grid, our approach is based on something that we call the state error. The state error can be represented in watts or in a percentage, And it's calculated by summing up all of the power consumptions of the different homes at a single instant in time. And then that summation is compared to a value that we take at the generator. It's taken by a meter that we call the totalizer or the aggregator. So I'm going to mention totalizers. That's what I'm talking about. I'm talking about the power generated. The state error is made up of a few components. There's, of course, non-technical losses, which is the thing that we're trying to sense. There's also the consumption of the meters themselves, which the meters do not actually sense themselves. So that has to be accounted for. And then there's other components, including line losses, sensor error, temporal sensing jitter, and finally, communication loss. So communication loss matters because we need to hear back information from every single meter. Otherwise, we can't do our comparison with zero error. The way that we model line losses is using a power systems tool called GridLabD, and then the rest of these are modeled in simulations, mostly with Gaussian distributions. For each of these components, we have 2 to 8 months of data collected that we use to simulate on top of. So one interesting thing is we found that the sensing jitter, which happens if you don't sample from the houses at all the houses at exactly the right moment, that can actually have a significant effect on your final results. So we found that it can be up to 2.5% extra error. So when you sample is very important. I have an example to convince you that sampling jitter actually matters, because not everyone always believes me. So on the top there, we have the state error over time for a grid simulation where the sampling jitter is 15 minutes. We see that it's very noisy. And then on the bottom, we have the same thing, but with sampling jitter with 1 second. So we see that in the bottom one, the places where we have NTL, energy theft, happening, it's much easier to figure out where, when in the day it's happening. You would never be able to do that in the top graph. Here's the design space version of that previous graph. It's the relationship of how often you sample, and which is related to the jitter and the state error. So what we can see is that as you expand, the size of your grid, you're being pushed to the right of this graph. So that's the direction that the scale is going. And one key goal of our project is to understand this relationship and figure out how to use time synchronization to push this relationship down, so push the overall state error down. One important way that we actually push that state error down is that we take advantage of the wireless network design. So we use a TDMA-based wireless protocol. This means that the timing of when the communication happens is very predictable. And this enables us to have millisecond level time stamping at every single meter. And it's also at scale. So we see that it's 400 plus nodes. On the left, we see that's the data link version of our grid. And on the right is the actual grid topology with the homes as red dots. In order to test out our model, we implemented a simple proof of concept NTL detector. So one thing that I haven't mentioned is that at the time of this paper, we didn't actually have real totalizer data, so we needed to figure out some other way of getting preliminary evaluations. So what we ended up doing is actually using our model to simulate the grid and then running a naive detector on top of that. What this gives us is it's the best case performance that we could see if we ran the naive detector in the real world. Our naive detector is pretty simple. It's calculated from a static value and a variable value. The static value is just the 2 sigma deviation of the state error, so that value doesn't really change. And then the dynamic value was just 1.5% of the total power on the grid. Here is an example of what the simulation output looks like. We have the amount of NTL, amount of energy theft, on the bottom in gray. And then above that, we have the state error as a solid line, and then the value of the detector as a dashed line. So you can see examples of NTL being detected on the left there, and on the right you see we missed that occurrence of NTL. Overall, we ended up seeing pretty reliable detection. So we were seeing numbers on the order of 0.4% of total grid power. So if theft is 0.4% of all the energy being consumed, that comes out to 38 watts out of 9 kilowatts being consumed on the grid. All right, so we thought that those numbers on the last slide were a little bit optimistic, and we have more recent numbers now, and it turns out that we were completely right. So since that paper was published, we have collected more data, and we found that line losses were much larger than they were in simulation. So we went there from about 5% to up to 25% on the real grid in Haiti. And we found that in the best case, we could only really detect 120 watts of theft. So that's a larger, significantly larger value. We've tried both model-driven and data-driven detection schemes, and we found that there's a trade-off between the accuracy of model-driven and the simplicity of the data-driven schemes. So I'll finish real quick with some of the lessons that we learned. We found that the modeling can be very useful, but you have to be very careful about your parameters, setting your parameters correct. That's what we think was right now was the problem with our modeling initially. We also found that the time at which you collect your samples can be even more important than the error in the sensor. So always watch out for that. And lastly, if you want to do energy theft detection, you really have to understand your sources of error. Thanks.